quantum mechanics, physical theories were what philosophers call deterministic. Determinism means that what comes before fully determines what comes after. The place of determinism in physics was illustrated by what's come to be called Laplace's demon, named after Pierre-Simon Laplace, the French mathematician. The idea is that if you had a thinker with a powerful enough mind and gave this thinker the true laws of physics and a complete description of the world and everything in it at one instant, this thinker could determine the state of every part of the universe at every time, future or past. The supposition is that the world worked that way. But then along came quantum mechanics. What is it and where did it come from? Well, at the end of the 19th century, we thought physics was pretty much done. With Newton's theory of mechanics and gravitation and Maxwell's theory of electricity, magnetism, and light, we thought we pretty much had everything accounted for. There were a couple of strange phenomena that we had to figure out, but that would soon be done and the book of physics could be written. One of those led to relativity, but a couple of the others led in a completely different direction. They were blackbody radiation and the photoelectric effect. The problem with blackbody radiation can be imagined by thinking about a hollow metal sphere. Now, if we heat it up, then it glows. Giving off light means getting rid of some of its energy. But now, suppose that we make the outside surface black, so no energy is lost there. Now, the inside will still glow, but the energy emitted inside the sphere will be reabsorbed by the sphere because it stays inside. But this reabsorbed energy would further heat up the sphere, causing it to further glow and give off more energy inside that would be reabsorbed. Like sitting between two mirrors and seeing the image go off to infinity, it seems like the energy inside the sphere would reinforce itself, increasing to infinity. But that means that by adding the finite energy needed to start the inside of the sphere glowing, the result would be infinite energy. Well, that doesn't work. But why not? A number of solutions were proposed, and each worked well for a part of the problem, but none gave the full answer. Max Planck, the biggest name in physics the generation before Einstein, decided to work the problem backwards. He started from the actual data for the energy at each wavelength of light as given for a particular temperature. He then tried to see what curve would fit. A theory emerged, but it required a weird mathematical move. He could explain everything if light was emitted and absorbed only in packets. Everything worked out perfectly if you made the assumption that light was emitted and absorbed in energy packets of the size E equals h nu, where nu is the frequency of the light and h is a constant called Planck's constant to make the units and numbers come out right. The amount of light that something gave off had to be E equals nh nu, where n is a counting number, 1, 2, 3. Those were the only amount of light you could have. Light was like eggs, not butter. Butter you can buy in any amount, but eggs have to come in ones. Right? You could buy half of any amount of butter, but you can't go to the store to buy half an egg. But that had to be false. Light is smooth. If you had a light on a dimmer switch and a steady enough hand, no matter how dim the light was, you could always make it half as bright, and half as bright, and half as bright. But to make the theory fit the curve, light has to work like a lamp with a three-way bulb, where there are only specific amounts of light that could be given off, with no amounts in between. Planck dismissed this as unreal, but took it as a necessary as if to make the math work. A second troubling phenomenon of this period was the photoelectric effect. Photo for light and electric for electric. It was found that if you take ultraviolet light, like from one of those black lights with the fuzzy posters from the 70s, and shine it on metal, then electrons are kicked out of the metal. We could explain that just fine with our old theories. But the weird part was that if you made the light brighter, our theory says that the electrons should come out faster. Increased energy in should entail increased energy out. But that's not what happens. When you make the light brighter, you get more electrons out, but all moving just as fast as they were with the dimmer light. Einstein figured out a solution, but it required Planck's assertion that light is emitted and absorbed in packets. If we think of the light not as a wave hitting the metal, but like little footballs, then making it brighter doesn't mean a larger wave shaking electrons free, but more footballs banging against the electrons, knocking them out of the surface. More light, more footballs, more electrons. So, we started to see a couple of anomalous cases solved with the assumption of quantization. By quantum, we just mean something that can be counted. There are lots of quantized entities that are in no way weird. How many chairs in a room? Count them. Chairs are quantized. They come in ones. There's never 23.2375 chairs in a room. What was starting to happen was that things we thought were continuous were having to be quantized. That's strange. The whole thing exploded when Niels Bohr saw that he had to make the same move with respect to the most basic element in the universe, atoms. Now, in the last lecture, we looked at how and why we believe in the existence of atoms. We left the story with atoms existing, but the tale continues. While we call them atoms, they really aren't, right? The word atom is Greek for uncuttable. The classical idea of an atom is that of the basic indestructible building block of nature that has no parts, but turns out it does. J.J. Thomson discovered the electron. There was a negatively charged particle that was a part of the atom. But the atom is electrically neutral, so if part of it is negative, there must be a counteracting positive part as well. But while he could make a stream of the negative particles, he couldn't do the same for the positive. So Thomson proposed the plum pudding model in which electrons were nuggets of negativity in a sea of positivity, like plums in Christmas pudding. But that picture was overturned by Ernest Rutherford. He took an extremely thin foil of gold and was shooting the negatively charged particles at it. He was looking at the angle of deflection. Well, he wasn't. His assistant Ernest Marsden was. The great ones come up with the ideas, and those of us who work for them do the grunt work. As Marsden was keeping track of the location of the flashes, sitting for hours in the dark, he noticed something bizarre. Every once in a while, every rare once in a while, the flash would be on the wrong side of the foil. It was as if the electron didn't go through the foil, but bounce off it like a ball hitting a wall. That couldn't be right. The particles were moving much too fast, and the foil was much too thin to be that hard. But Rutherford took these anomalies seriously and realized that the positivity was not spread out, but concentrated in a very small region. When an electron hit one dead on, which would be very infrequent since they were so small, it would bounce backward. Rutherford had discovered the nucleus. For this, he was awarded the Nobel Prize in chemistry. He joked that the fastest reaction in nature was his transition from a physicist to a chemist. So, we have small, light, negatively charged electrons and a small, dense nucleus of positive charge. This gave rise to the solar system model of the atom we all learned in grade school, where there are protons tightly packed into the nucleus with uncharged neutrons to give the atom its mass, and electrons moving around the nucleus at various distances to give the atom its size. The tiny looks like the large. The symmetry was delicious, and physics could be done. Except that it can't be true. If electrons are negatively charged and moving around the nucleus, the atom would be unstable. If you move something charged, it creates a magnetic field. Moving electrons would be constantly giving rise to a magnetic field around the atom. This takes energy. So the moving electron would be constantly giving up energy. This should mean that it would circle around at smaller and smaller distances until it crashes into the nucleus. If the solar system model of the atom was true, then every atom in the universe should be instantaneously imploding. So the theory had to be wrong. So how do we build stable atoms? The answer Bohr discovered was to quantize energy. Electrons could only be in specific tracks around the nucleus. They could not orbit at any old distance. There were specific tracks, and they had to be in one of those tracks. They could move from an inner track to an outer track if the atom took in exactly the right amount of energy. But, and this is the really weird part, it would move from the inner track to the outer track and never have been at the points in between. And similarly, it could move from an outer track to an inner track, thereby giving off the exact difference in energy between the two as light, but never have been at the points between the two tracks. This solved another lingering problem. Chemical elements had fingerprints. Heat up, say, sodium, and a specific set of frequencies of light would be emitted. The light that came out wasn't spread out smoothly across the spectrum, but definite, specific sets of colors. Why? Well, the answer was obvious if each type of atom had its specific tracks around its nucleus. It could only absorb exactly the amount of energy necessary to move between its specific tracks, and it could only emit energy in those amounts. Those amounts of energy were emitted in packets corresponding to the difference in the energy levels associated with the tracks. In the basic component of all matter, the smooth was becoming discrete. We had physical entities, electrons, moving in a way that can't be described by our mechanics. That is, our theory of motion. We needed a new theory of motion, a new mechanics that would account for this quantization. We needed a quantum mechanics. This became the project for physics. Bohr had an assistant, Werner Heisenberg. Heisenberg was one of those guys in high school you wanted to hate, but you couldn't because he was just too perfect. Tall, handsome, blonde, muscular. He was an expert skier, and he was also a genius. He lived in the Bohr's attic. To Bohr, this meant that Heisenberg was permanently on call. Bohr would bang on his door to discuss thoughts he had about quantum theory. They were developing at 2, 3, 4 in the morning without thinking. Bohr was obsessed, and he thought Heisenberg should be too. Fortunately, he was. That obsession paid off when Heisenberg figured out a way to take all the strange results that were coming out of atomic physics and structure them in a mathematical system. The trick, Heisenberg realized, was that you had to generalize the notion of an observable property. Usually we would use a number to represent the value of a property. The length of a bridge is 15 meters. The mass of a liquid was 5 grams. Other properties needed vectors. That is, ordered triples of numbers, each a number for one of the perpendicular directions. But Heisenberg realized that to do quantum mechanics, you needed not just a vector, but a matrix, a rectangular array of numbers, or even a stack of rectangular arrays of numbers. And some of these stacks would require an infinite number of rectangular arrays of numbers, infinite dimensional matrices. The math was now so difficult that it was nearly impossible to use. This made Heisenberg happy because if the theory was hard to discover, it ought to be hard to use. But what made it even harder was that some of the matrices behaved strangely. Now, there are versions of our standard arithmetic operations on matrices. We can add them, subtract them, multiply them by a number or by another matrix. But when it came to multiplication, there were certain pairs of properties that forced us to change the basic rules of matrix arithmetic. Now, multiplication is supposed to be commutative, right? You could change the order of the numbers you're multiplying and still get the same result. 2 times 3 is 6. 3 times 2 is 6. Heisenberg realized that in quantum mechanics, there would be strange pairs of properties whose matrices did not follow the usual multiplication commutative relation. For position, there was momentum. For time, there was energy. It seemed like most properties had a frenemy. They were tied together and couldn't be separated, but each was always trying to undermine the other. This is the basis for what's become known as the Heisenberg uncertainty principle. There are pairs of physical properties such that observation of one that is, the determination of the parts of its matrix, disallows the determination of the parts of the matrix of the other. The more exactly you know one of the pair, the less exactly you can know the partner. Now, we have to be careful here. Heisenberg's uncertainty principle is often wrongly explained to be an epistemological instead of a metaphysical uncertainty. Remember that epistemology is the study of knowledge. It's about what we can know. Metaphysics is the study of reality. It's about what really exists and its actual properties. The Heisenberg uncertainty principle is about what is, not just about what we can know. The usual pair of frenemies we discuss is position and momentum, or velocity if we set the mass to 1. The idea is that the more exactly we determine the position to be, the less exact of a velocity the particle has. It's not just that by measuring the position we know less about its velocity. It's not about our knowledge. It's that the more exactly we determine the position, the less of an exact velocity it actually has. It has, in reality, a range of velocities, one thing moving at an indeterminate speed. And the same in the other direction. The more exactly we know the velocity, the less the thing actually has an exact position. The weirdness about quantum mechanics is deep. It means that the more exactly we know a particle's velocity, the more spread out the particle is through space. If we know its velocity exactly, then it fails to have an exact location. It is, in a strange way, spread out throughout space. This led to one of the classic physics nerd jokes. So, Werner Heisenberg is driving to work when he gets pulled over by a police officer. The cop walks up to his window and says, "Do you know how fast you were going?" Heisenberg looks up and says, "No, but I know exactly where I was." The police officer says, "You were going exactly, 100 miles per hour?" "No," shouts Heisenberg. "Now I have no clue where I am." Much to Heisenberg's chagrin, the Austrian physicist Erwin Schrödinger did away with the need for his infinite-dimensional matrices. Schrödinger came up with a simple second-order differential equation, the normal sort of equation physicists seem to always use for everything, that turned out to be exactly equivalent to Heisenberg's matrix mechanics. The Schrödinger equation captured everything the matrices did, but had the great virtue of being easy to use. But easy to use and easy to understand are two different things. The Schrödinger equation is the state equation of the theory of quantum mechanics. That is, it's the equation that governs the state of a quantum system. State equations have state variables, that is, the variables that show what the relevant properties of the system are. Now, for Newtonian mechanics, the state equations are the equations of motion, and the state variables are mass, position, velocity, and acceleration. Tell me those things about the system, and I can use the laws to tell you how the system develops over time. For quantum mechanics, the state equation is the Schrödinger equation, and it contains only one state variable, which we represent with the Greek letter psi. Why psi? Because when you ask physicists what it means, they go, what is absolutely peculiar about quantum mechanics is that when you solve the Schrödinger equation for a particle in a specific physical context, you need to pick an observable in which to couch psi. And what comes out as the state of the system is not what we expect. We expect a single value for the property. But what the equation gives us is a sum of every possible value that the property could have multiplied by a coefficient between 0 and 1. Now, when you see numbers between 0 and 1, mathematically, you begin to think probability. And it turns out that's exactly what they are. The coefficients are measures of the probability that the particle will be found to have that value of the property if the property is measured. So, if we have a particle in a situation that has a certain potential energy associated with it, we can work out the Schrödinger equation for it in terms of, say, position. The equation doesn't tell us where the particle is. It tells us where it could be and the likelihood we will find it there if we look. The result will look like this. Psi equals a sub 1 psi sub 1 plus a sub 2 psi sub 2, and so on, where each psi is a possible place the particle could be. And if we do the experiment over and over and over again, we find the particle in a different place each time, and the percentage of times we find it at each specific spot is perfectly given by the coefficients. Albert Einstein thought that the universe is a deterministic place. Every particle has a complete set of values for all its properties at every instant, and the true and complete laws of physics will show how they relate to each other. Einstein felt that the Schrödinger equation might be right as far as it went, but it didn't go far enough. Quantum mechanics is incomplete. The probabilities from the Schrödinger equation show the probability of finding the particle at this point, but it was either at that point or not at that point. The uncertainty inherent in the theory, Einstein thought, is epistemological. It's about how much or little we can know about the properties that the system has. That's why Einstein said God does not play dice with the universe. He meant there are no metaphysically probabilistic elements in reality. Probability is always the result of us just not knowing everything. But it turns out that it's not epistemological probability, but metaphysical probability in quantum mechanics. Before we observe it, the particle does not have a position. It's in the combination of all the positions, what we call a state of superposition, or its superposed state. The Schrödinger equation is a law of nature. It does fully, not partially, describe the state of the system. But we never see things in these superposed states. When we measure them, they always have one particular value for the property. We never see particles spread out through space. They're always somewhere or other. This is what we call the measurement problem. Before we perform a measurement, the particle is in its superposed state, as dictated by the Schrödinger equation. But when we look at it, the solution of the law of nature goes away, and the thing has a single definite property value. Why would a law of nature only hold for the universe when we don't look at it, but fail the instant we do? This allows us to fully account for the uncertainty Heisenberg discovered. When you solve the Schrödinger equation for a particle in a situation in terms of position, you get a string of all the possible positions multiplied by probabilities. When you do it in terms of velocity, you get the same sort of thing, a string of all the possible velocities, each multiplied by a measure of the probability. When you measure its position, the superposition collapses to a single value, but you can't know which it will be. But doing that puts the particle in the full superposition in terms of the non-commuting observable partner. Collapse the solution in terms of position, and you expand it in terms of velocity. Collapse it in terms of velocity, and you expand it in terms of position. The Schrödinger solutions are not uncertain because these have values we don't know. The mathematical combination is the actual state. Let's get a handle on how exactly bizarre this is. It not only challenges our common sense, it undermines the fundamental principles of our logic. Classical logic, going back to Aristotle, was based on what we call the principle of the excluded middle, that says all sentences have one of two truth values, true or false. Take the sentence, I have a brother. You might know or you might not know if it's true, but it is either true or false. It has to be one or the other. It can't be both. But with the weirdness of quantum mechanics, the laws of physics are demanding that we give up that foundation for rational thought. Take the sentence, the particle is at position 5. If I observe the particle, then there are two possibilities. If I look at position 5 and it's there, then the sentence is true. If I look at position 5 and it's not there, then the sentence is false. But if instead of measuring the position, suppose I measure the particle's velocity, that means it's now in the superposed state with respect to the non-commuting observable position. So, if it's in the superposed state of being spread out through all possible values probabilistically, is the sentence, the particle is at position 5, true or false? It's not quite true, but it's not quite false. But according to the principle of the excluded middle, it has to be exactly one of those two. But it isn't. Quantum mechanics broke logic. But logic is the tool of the philosopher, so philosophers tried to fix it. For this, we'd need a new logic for quantum mechanics. The person most associated with this project is John von Neumann. Von Neumann is most well known as a mathematician and as a physicist. He's one of the founders of game theory and one of the first members of the Institute for Advanced Study in Princeton with Einstein. And he was also the first to break their rules concerning no experiments. The Institute was supposed to be at home for theoretical work, but von Neumann had a project he wanted to carry out. It turned out to be some of the first work on what would become computers. It's less well known that in college, von Neumann was fascinated with philosophy. Indeed, he studied with Edmund Husserl, one of the towering figures of 20th century philosophy, as the founder of the movement that became known as phenomenology. In thinking about the relationship of the new quantum mechanics to the old logic, von Neumann realized that we could possibly fix things with the addition of a new truth value to augment true and false. We can call it indeterminate. Consider the logical connective OR. Right? OR connects two sentences, call them P or Q. An OR sentence is true when either of the sentences connected by OR happens to be true. So if I say Bob has sugar or cream in his coffee, then I've spoken truly if either Bob has sugar or Bob has cream in his coffee or both. I would only be wrong if he had neither. But now, let's think about how complicated a simple OR sentence becomes with a third indeterminate truth value. We no longer just have 4 possible cases of true, 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 false, false, true, and false, false. We now have 9 possible cases to consider. All the original cases are still there, but what about true or indeterminate, false or indeterminate, indeterminate or indeterminate, and so on? Now we know that an OR sentence is true if either of the connected sentences is true. So, true or indeterminate and indeterminate or true are both true because it doesn't matter whether the indeterminate sentence turns out to be true or false. Common sense tells us that indeterminate means it could be true, could be false. So, false or indeterminate means that it might be false or true, or it might be false or false, so we don't know. So, indeterminate or false, and false or indeterminate would have to be indeterminate. Just one case left. Again, common sense tells us that indeterminate or indeterminate means that either could be either. So, surely that means the last one is also indeterminate. But this is quantum mechanics. Common sense doesn't necessarily apply. Suppose that we have a property that has only 2 possible values, right? Well, one example is what physicists call spin. It has 2 possible values up and down. If the particle we're considering is in its superposed state, and P is the sentence, this particle is spin up, and Q is the sentence, this particle is spin down, then both P and Q will have the truth value indeterminate because the superposed state makes this indeterminate. But what do we know about the particle? It is either spin up or spin down. Those are the only 2 possibilities. So what do we know about the sentence P or Q in the case where both are indeterminate? It has to be true. Yes, it is a weird logic. And it only gets more and more complex and more strange the more von Neumann and those who followed worked on it. But if the world is that weird, and according to all of the observable evidence we have in testing quantum mechanics, it is that weird, then the reasonable way of just thinking about it has to be just that weird too.